David Crumley. This is going to be my demo for my EGN 4060 Introduction to Robotics project. So the inspiration behind this project was basically I was very interested in the labs that we were doing in the ROS. So I figured I wanted to build that myself with my own custom robot model, URDF model, and build all the packages and build everything from scratch. This way I could get a really good understanding of exactly how that works, and I feel like that's a very important thing because I'm going to be using use my URDF modeling. I used differential drive controller. I used G mapping, SLAM, which is the G map. The G mapping knows is doing SLAM. I'm using Monte Carlo localization after the map is already created. I'm also using some path planning to avoid obstacles using cost maps and trajectories in order to reach a certain goal. And so it basically encompasses everything, and I built everything myself, and it was a great project. And I plan on also building a physical robot using this same software, just build some hardware interfaces for it. So let's go ahead and get started here. If we ROS launch project, and we will start with the Explorer launch. Right, as we can see here, the Explorer node has started. We have a map already being created by the G mapping SLAM node. We can see in Gazebo what's happening in the simulation is the same thing that's happening in the RViz. We can also see that the laser, these little green dots, are the laser scan data, and they are snapping to the map. So our localization is working, our mapping is working, which is great. So these maps come out very well. We will see later on, using with the Monte Carlo localization, using the pre-made map, that there are some issues with rotation. We can kind of see them here, but they resolve themselves very quickly, and it doesn't result in any sort of collision or bad movements. And so this thing, it'll just move around randomly. It's a pretty simple algorithm. It just does, it takes the laser scan data, and depending on where the laser scan data is being read from, it will make certain decisions. It'll either curve either direction or rotate in either direction or move forward. Now we see that our map is looking pretty good. We can go ahead and stop this part of the algorithm and save the map into our project directory. So as you can see, we're in a maps directory within our project workspace. So we'll go ahead and run the map saver. We'll just save it as map. Okay, now that we have our map, we can go ahead and run the routing algorithm, which basically takes the map that we created, and it uses some pathfinding tools to find a path using the cost map of the obstacles that were found from the G mapping. So ROS launch rounds. Alright, so now we have our maps, our map generated, and we have our Gazebo simulation back up. Now we can see there are some more graphics on this this map, and these are generated by the cost map. So basically what these are doing is they're setting boundaries for the robot. It takes the map created from SLAM, and it takes the parameters that you give it and basically creates boundaries for places that that the robot can't go, because if it goes to these places, it will be hitting one of these boundaries. We also have here this cloud of green arrows. These are the Monte Carlo's localization. It's basically saying it thinks we're in one of these arrows. It's not very confident yet because we haven't done anything, we haven't moved anywhere. But if we set a movement goal here, we get new laser scans and compare them with our map, it'll get more confident as it goes. You can see the cloud getting smaller. And now it knows exactly where we're at. The laser scans are matching up with the map now, so we know we're in the right spot. The only issue I'm still having with this, like I mentioned before, is the rotation. So if we send a simple rotation command, or basically just send it to somewhere that's not a straight path, it loses its orientation, its odometry. So these are the things that I'm going to continue working on, as well as the hardware interfaces for the physical robot. Alright, so now I'd like to just show you the organization of the project itself. So we can go ahead and jump to the package, go to raw CD, Robo project. And from here we can use something called tree to get a good view of what it looks like. So the first directory we see is the config directory. This holds all of the YAML parameter files. These are needed for almost all the nodes. They all configure each node specifically to work for the robot that I've created. So each one is going to be used by these launch files and the nodes that are launched by those files to act accordingly to what I need them to do. Then we have our launch directory. This launches all of the nodes. The Explorer launch that we launched first is a combination of the Wander, the Gazebo, which launches Gazebo, the Display, which launches the RViz, and the Control, which launches the diff drive controller that I've configured for the skid steer. It also launches the joint state publisher and the robot state publisher. The AMCL launches the Monte Carlo localization. We also have a teleoperation, which I haven't used, I don't use anymore, but I use it for testing. And I wrote in all of those source codes myself through C++. So we also have our maps folder. That's where the maps goes that we saved earlier. The meshes is only the LiDAR scanner. I pulled a mesh from that just so it looked a little more like the actual thing. Package.xml, that's our macro file for the package itself. Nav.rviz, that's the configuration for RViz. That's why when I run the launch files, everything pops up already ready to go. It uses that file to know what to show me. So we also have the robot model. That's the model that I created. Created all the joints, the transmission elements, and all the Gazebo plugins are in there as well. And then our worlds are just all the different worlds that we've used for Gazebo. And that is pretty much it. Thank you for your time.